Well, hello and welcome back. In this video, we're going to go over section 1.2, which is talking more about angles and how they're related and a little bit with triangles. So the first thing that I'm going to go over, and y'all can choose to participate in this or not, this little activity here, it's just to prove a point. And this is a point that you've probably been told a million times and just taken it for granted that like, oh, okay, well, I guess that's fact. And you maybe have never seen why it works. So I'm gonna move this down to the bottom of the screen and it says cut a triangle out of a piece of paper. So what you can do is you can just take a piece of printer paper, piece of notebook paper, and cut it along the diagonal. Okay, however you want to make a triangle. I have a triangle here. And then it says label the angles A, B, and C. For each vertex of the triangle, draw an arrow pointing at the vertex. So I'm going to go ahead and label, whoops, this one A. I'm going to label this one B. I'm going to label this one over here C. Oop, can't hardly do it. All right. And then it says with two cuts, we want to separate the triangle into 3 pieces. So what I'm going to do is I'm just going to rip it because, well, I don't have scissors right on hand. I'm just going to rip off this corner and I'm going to rip off this corner, right? Because that will create 3 pieces, okay? Give me just a second. Doesn't have to be pretty. All right. So there's my triangle in 3 pieces. And the next thing it says to do is to line up the angles A, B, and C side by side. So I'm going to move this paper down. So here's A, and here's B, or sorry, here's C actually. Doesn't really matter which order you do it in. Notice when I line up, I'm trying to do this straight for the video. Ah! Oh my gosh, my hands are so shaky. All right. I can't get it to stay. It keeps trying to stick to my hands. I just put on lotion. All right. So when I put all the angles, all the little vertices of my triangle together, notice we can easily see what they would add up to, right? Oh, I thought that would hold it down. Maybe not. Struggle busting to hold these together. Okay, so when we put all the vertices together, A, B, and C, notice we can tell what the sum of their angles would be, because if I add this angle plus this angle plus this angle, notice it creates a straight line, right? It makes a perfectly straight angle. And if you remember from section 1.1, a straight angle is a perfect 180 degrees, right? This would take exactly 180 degrees to make this straight line. So what's cool about that is that we basically proved that the addition of all 3 angles within a triangle will always sum to 180 degrees because we did not specify what these angle measures had to be, right? You could take any triangle and rip off 2 ends and put all 3 angles together and it will always come together to make a straight line. That's kind of a fun thing to try if you want to test the theory. And I know most of you have heard that the sum of all interior angles add to 180 degrees, but that is something that we will use many times, okay? So anytime we have a triangle, and you can draw it however you want, whatever kind of triangle, this is A, B, and C, we know that A plus B plus C should equal 180 degrees, okay? All right, the next thing I want to introduce you to, that was just kind of a fun proof of something that hopefully we've heard of before, but I do want to introduce you to vertical angles. So this may be something new. So vertical angles is when you have 2 intersecting lines, not necessarily at 90 degrees, just any intersecting lines. I'm going to go ahead and just I'm just going to number these angles so that we can kind of reference them. So let's call this angle 1, angle 2, angle 3, and angle 4. When we talk about vertical angles are the ones opposite one another. Okay, so this means that like angle 2 and angle 4. And my little notation to write an angle is like that. So I'm going to say that angle 1 and angle 3 would be vertical angles, right? And angle 2 and angle 4 would be vertical angles, okay? Because these are opposite one another, and then these are opposite one another, okay? So what we want to show is that vertical angles are equal in measure. This is something that we're going to use to help us solve things in the future, okay? Vertical angles are equal in measure. So we want to show why. How do we know that, right? Because Miss Williams said. So I'm going to show you, if I pick any two of these angles, they create a straight line, right? So let's just pick, let's say, angle 2 and 3. If I add up angle 2 plus angle 3, that creates a straight line, right? From this line to that line, it's 180 degrees. So I'm going to go ahead and just say angle 2 plus angle 3 adds up to 180 degrees because it creates a straight line, right? And the same thing could be said if I chose, say, angle 3 and angle 4, right? If I started at angle 3, I could say angle 3 over here to angle 4 is also 180 degrees. Angle 3 plus angle 4, right? So what I'm going to do is that if I know that angle 2 plus angle 3 equals 180, and angle 3 and angle 4 equals 180, then that means these two things have to be equal, right? So I'm going to go ahead and just say, so this means that angle 2 plus angle 3 has to equal angle 3 plus angle 4, right? And then if we were to use any kind of solving method, right, notice I have an angle 3 on each side, so that cancels, because if I were to try and, say, subtract this over, they would cancel out, right? So I'm going to go ahead and just drop those, and notice what we're left with is that angle 2 is equal to angle 4. So what we've shown is that these vertical angles are equal to each other in measure, right? And the same thing, we could do the same proof to show that 1 equals 3, right? We could say, you know, 2 plus 3 is 180 and 1 plus 2 is 180, and by the same reasoning, prove that. Okay, so this is something that we just want to keep in mind because we'll use that to solve. I'm not going to require you to write out this proof. I just like to show you where it comes from and why it's true. Okay, the next thing that we need to know about is we have a couple of, well, let me explain what transversal is. So any line intersecting two parallel lines is transversal. If you've taken geometry, you may have seen some of this stuff before. So I'm going to write two parallel lines. Remember, parallel lines never touch and they never cross, right? Because their rate of change is exactly the same. So I'm just going to say these are two parallel lines. Okay, and a transversal line is any line that intersects these two. So it could be like this, right? It could be going the other direction. I'm just going to write it like this for right now. Okay, so what we're going to look at on the next page is when we have a transversal line, we have a few things that we can claim, a few more facts about how these angles, these four angles, are related. Okay, so let's look at the first one. The first one, and actually I'm not even going to turn the page. I'm going to talk about it right here because it gets confusing on the next page. So I just want to talk through this. Let's pretend for a hot second. Let's call this angle alpha and this angle beta. Okay. So we know by vertical angles, this one would also have to be alpha, right? And this one would also have to be beta. So what I'm going to claim is that if I add these two lines together, or sorry, these two angles together, alpha and beta, it should equal 180, right? Because this line, if I got too much of the same color. If I add this alpha and whatever this angle is, it's got to be 180. And if I add this beta with this, whatever it is, it's got to be 180, right? But I also know that this beta plus this number has to be 180. So when I work my way around, I pretty much have proven that this must be beta and this must be alpha, right? I know we've seen stuff like this in geometry before, but the main thing that I want to point out is that if alpha plus beta is less than 180 degrees, then these are not parallel lines. Then lines not parallel, okay? These two angles have to add up to exactly 180 degrees in order for these lines to be parallel. Because if this happens to be less than 180, then that means these lines have to be slanted at different angles, right? Because we know that these two have to add up to 180, these two have to add up to 180, right? These two have to add up to 180. So we have to have all the same vertical angles. If it's less than 180, the only time that that could happen is if these two lines are not parallel, okay? Now, again, I'm not going to ask you to prove that. I'm just pointing it out to you, because what we have on the next page is basically what we call a parallel postulate, right? And it's basically explaining what I just showed on the last page. If a line cuts two lines and the interior angles on the same side sum to less than 180, then the lines have to intersect, okay? So if I have these two lines, and we're saying this is alpha and this is beta, we're saying if alpha plus beta is less than 180, then the lines intersect. Okay, it means they're not parallel. Okay, so this is going to come in handy to know, but hopefully we're always working with parallel lines so that we can do our adding up to 180, because that will help us. Okay, all right, so here's the fact we're looking at now. The fact that we want to show is that alternate interior angles are equal in measure. So let me show you what an alternate interior angle looks like. I'm going to go ahead and draw my two parallel lines, my transversal line, and I'm going to number these. I'm going to say this is number 1, number 2, number 3, and number 4. So interior angles means that they all fall between the two lines, okay? Alternate means that they're opposite. So what that means is that I am hoping to show that this angle number 2 is the same as this angle number 4, right? And it makes sense because if 1 and 2 have to add up to 180 degrees here, right, it would make sense that 3 and 4 also have to add up to 180 degrees. So what I want to show is that angle 2 and 4 have the same measure, and then we can assume, or by the same reasoning, deduce that angle 1 and angle 3 also have the same measure, okay, which is what this fact is stating. Alternate interior angles are equal in measure. So I'm actually going to prove this by a contradiction, okay? I'm going to assume they're not the same. Okay, let's just assume one's bigger. Or let's say 2 is bigger. Okay, so we're going to say angle 4 is smaller, and I'm going to just use less than, okay, is smaller than angle 2, right? We're just going to assume this. Proof, I should have wrote this over here. Proof by contradiction. Okay, so we're going to assume that angle 4 is smaller than angle 2, okay? Well, if I add something to both sides, no matter what I add, right, by the rules of equality, this side should still be smaller than this side. So I'm going to go ahead and just add in an angle. I'm going to add in specifically angle 1. So this means that angle 4 plus angle 1 would still have to be smaller than angle 2 plus angle 1. Right? If I just add something on both sides, it's not going to magically make this side bigger than this side, right? Because I'm adding the same amount. So it's like saying 1 is less than 5. And if I add 10 to both sides, 11 is still less than 15, right? Okay, are you with me? All right, so what I know about angle 2 and angle 1 is that they make up this parallel line right here, right? angle 2 plus angle 1 has to total 180 because it creates this straight angle. So I know that this equals 180, right? So now what I've shown is that angle 4 plus angle 1 is less than 180 degrees, right? And that is where I get my contradiction. So the way we show a contradiction is we show two arrows contradicting. So it's like this one's hitting this one. Contradiction. Okay? Because by the parallel postulate, we showed that if two angles are added together and they're less than 180, then those lines have to intersect, right? And so here, that doesn't work. That's a contradiction. It's not true, right? By this parallel postulate, the lines intersect. And we know that they don't intersect because we set them up to be parallel. So this is where we get our contradiction. So we've shown that 4 cannot be less than 2. And then I'm just going to say, similarly, we could show that angle 2 is less than angle 4, right? We could, because here we assumed that 4 was smaller, then we could assume that 2 is the smaller one, right? We're still going to get something that's not true there if we work it out using the same reasoning. So if 4 is not smaller than 2 and 4 is not bigger than 2, then basically we're proving that angle 4 has to equal angle 2. Okay? So what that's telling me is that alternate interior angles are always equal in measure. Okay? So that means that 2 and 4 would be the same. That also means that this angle 3 and this angle 1 are going to be the same. Okay? So I'm highlighting these facts. These would be good things to write down on a note card or a study sheet so that you have a quick reference to it when you're getting ready for the test. Okay? Here's another fact, and this is one that we solved with our little ripped paper at the beginning of class, right? It says interior angles of any triangle sum to 180 degrees, you know, and we want to know why. Okay, I'll show you, because now that we have these theorems, we can actually prove it. Let's say we have two parallel lines, right? And then let's say now we have two oh, this doesn't look very parallel. Sorry, kind of crooked. And then let's say we have two transversal lines. Let's make our first transversal line like this. Let's make our next transversal line like this. Notice what I created inside here is a triangle, right? So let's just go ahead and label these angles. If this is angle 1, 2, 3, then we know that this one that we just proved, our alternate interior angles are equal in measure, right? We know that these three add up to 180, right? Because these are the angles that make up the straight line. But we know that here's angle 3 up here. So our alternate interior angle would mean that this is also angle 3, right? Because this is our transversal line. This one's on the inside, on that side of this line. This one's on the inside on this side of the transversal line, right? Okay. Then similarly, we can do the same thing with 1, right? If this is angle 1 of this transversal line, then on the other side, this would be the same as angle 1, okay? So here, right here, we're showing that angle 1 plus angle 2 plus angle 3 equals 180 degrees. And then by these alternate interior angles are equal in measure fact, we can show that these are the same, these are the same. Therefore, all of these add up to 180 degrees. Okay? Are you kind of with me? I know it's a lot of talking, and it's probably easier to see than it is to explain. All right. So let's look at how we're going to use this, why this comes in handy, and why we care. Okay, we might be given a problem like this, where it gives us 3 of the interior angles of a triangle and asks us to find the third one. So we know that this angle is 70, we know that this angle is 50, and we don't know our third angle. Okay, so the way that we can solve that is we can just set up an equation because we know the sum of all interior angles is 180. So that means that angle A plus 50 degrees, right, that's my next angle, plus 70 degrees, which is my next angle, has to total 180 degrees. And now this is something I can easily solve for the measure of angle A. These are like terms, so I can just add them together. So angle A plus 120 degrees equals 180 degrees. And then I can subtract that across. So angle A is equal to, when I subtract 120 from 180, I'm left with 60 degrees. So I've solved for the missing angle. Okay, so easy enough, right? All right, so I do want to go ahead and go into some of our triangle properties that we might be dealing with in this class. So the first type is the types of triangles based on their interior angles. Okay, so we can categorize triangles in two ways. We can categorize them by the angles inside the triangle, or we can categorize them by the lengths of the sides. Okay, so these first three are categorized based on the angles inside of them. Okay, and the first one is an acute triangle. Okay, an acute triangle is where all interior angles are acute. Okay, so if you remember back in the last section, acute angles are less than 90 degrees. Okay, so a good example of an acute angle would be this one we just did, right? Good example. Because notice every measure is less than 90 degrees. This one's 70, this one's 50, and we just found out that one is 60. Okay, so that's what an acute triangle looks like, is all the angles are less than 90 degrees. Okay, the next type we have is a right triangle, and I think everybody knows what a right triangle is. We know that one of its interior angles is 90 degrees, right? We're super familiar with these because we've dealt with the Pythagorean theorem and things like that. Okay, and it could look all kinds of different ways. The only stipulation is that it has at least one interior angle that is, well, only one interior angle that is 90 degrees. Okay, and then an obtuse triangle is one where one interior angle is obtuse. So remember, an obtuse angle is larger than 90 degrees and less than 180. Okay, so it opens up more than a 90-degree angle, but it doesn't open up all the way to where it's a flat line, because then we don't have a triangle. Okay, so an example of an obtuse, let's see, let's pretend this is like my x-axis. So 90 degrees would be straight up, so obtuse would be over here somewhere. Okay, so notice like this would be where 90 degrees is. This would be like where 180 degrees is, right? So it's somewhere in between those. Okay, so this is my obtuse angle. Okay, all right, so that's how we categorize our triangles based off of the interior angles. Now we want to look at how we categorize our triangles based on the lengths of their sides. And I know we touched on this really briefly if you took my college algebra course or a college algebra course at ENMU. All of them should touch on this. But I know I covered it. If you took my course, you've seen it before, okay? All right, so types of triangles based on the lengths of their sides. The first one is an equilateral, I can't say it, equilateral triangle. And what we know about an equilateral triangle is that all the sides have equal length, okay? All the sides have equal length. So this side is the same as this side is the same as this side. And interestingly enough, in order to have an equilateral triangle, another neat fact is that all the angles, all interior angles are the same, right? So this would be like what? If they have to add to 180, so this would be like 60 degrees, 60 degrees, and 60 degrees, right? So even though we're basing it off of the outside lengths, this is just an added bonus that all interior angles are the same as well, okay? And isosceles, so here's how I remember this. So equal, equilateral, it's easy to remember, they're all equal. They're all the same, right? Isosceles is you say, I saw it. Isosceles, I saw it. And when you see things, you see it with your two eyes, right? So an isosceles triangle has two sides of equal length. So it might be something like this, where this side and this side are the same, right? Or it might even be like a right triangle. See if I can, that's not a very good drawing, where maybe this side and this side are the same, right? So an isosceles, if you saw it with your two eyes, right, it has two sides of equal length, okay? And then the last one is our scalene triangle. And the way that we categorize our scalene triangle is that it doesn't have any equal sides, right? This one is they're all equal. This one is two of them are equal. This one is nothing's equal. So this might be something like a triangle that looks like this. I'm sorry, my triangles are a little wonky looking today. Or it could be something that looks like that. Or it could be a right triangle, right? Right? Any type of triangle where all three sides are not the same length. Okay? All right. The other ways that we're going to solve is using ratios. Okay? And ratios we get from what we call similar triangles. Okay? Now, when we talk about similar triangles, the corresponding angles have equal measure and the corresponding sides are proportional. Okay? So what that means is we might have a triangle like this, right? And then like a smaller version of it where all the angles are the same, but maybe the sides are different, but they're proportionately smaller. They, this one relates to this one. The hypotenuse relates to the hypotenuse, okay? And this could go for anyone. It doesn't have to be like a right triangle. It could be a triangle like this, that's proportionate, right? Or you might even see where they draw a triangle inside of another triangle. I am stinking at drawing triangles today, aren't I? They might draw something like this. Okay, so what you see is that you have this outer triangle. See if I can draw it better the second time. You might have this outer triangle, right? And then within that outer triangle, you have a smaller triangle. And you know that these are similar triangles because the lengths of their sides are increasing or decreasing at the same rate, and they have all the same angle measures. Okay, so what I mean by that is if this is big A, right, big length A, then this would be little length A. If this is big length B, then this would be, little length B. And if this big hypotenuse is C, then, this would be little c. So we can come up with these ratios of how they're related. So we could say like big A is to big B. Big A is to big B the same as little a is to little b, right? Or we could say big A is to big C as little a is to little c, right? Or we can use B and C. It doesn't matter. We use big B is to big C as little b is to little c, right? So these are ratios that will help us solve for unknowns. So on the next page, I want us to look at a few examples of solving for unknown sides and unknown interior angles based on what we've learned so far, okay? All right, so let's look at this first one. It says, assume the two triangles are similar. Solve for little s and little t, okay? So I need to find some kind of ratio that helps me here, okay? So I need to find little s and I need to find little t. So I'm looking for this side length, right? And I'm looking for this side length. Okay. All right. So let's look for a ratio that helps me find little s. Okay. If I want to find little s, let's see, little s on this triangle is related to the same side, right? So little s and 4 are related. So I could say for my ratio, little s is the same as 4, and then I just need to set it equal to another ratio from these same triangles. So I'm going to go ahead and just pick this side. I'll pick this side. Okay. So that means on this triangle, I need to use 3 and 9. Okay. Now S came from the big one, and I wrote it on top. So my other one that comes from the big one also needs to be written on top. So this is going to be 9/3. Okay. If you do not understand where I'm getting these ratios, make sure you text me or email me and clear that up. Otherwise, this section's going to be bananas for you. Okay. So we're solving for S here. So in order to solve this, I can multiply both sides by a least common denominator, or in this case, I could just cross multiply, right? So if I cross multiply, S times 3 is 3s. And I always put little thingies on my s or use a cursive s so it doesn't turn into a 5, right? All right, so s times 3 is 3s. 4 times 9 is 36. And then I can go ahead and get rid of that 3 by dividing it off. So that means that s is equal to 12. Okay, so I know that this side is 12. Okay. All right. So now that I've gone over that one, what I'd like for you to do is I want you to try and solve for t. Okay. And then I would also like for you to try and solve this bottom example down here. So I want you to go ahead and pause the video and work on those. And when you're ready, unpause it and we'll go over them. Okay. All right. Let's go ahead and see how you did. Finding t, we need a ratio. So we need the side that corresponds to the t side, which would be 5 on the smaller similar triangle, right? So I'm going to say t is to 5 as, and I'm going to pick another side. Now, I will note, you could use 9 and 3 here, or you could use 4 and 12, now that we know what s is, right? You could use 4 and 12, or you could use 9 and 3. You should get the same answer either way, but in the event that you made a mistake on this one, if you use the one that you found, it's possible you might make a mistake on this one even if you work it correctly. Does that make sense? So I always try to use the ones that they provided, because I know that those don't have a mistake, whereas the one I solved for, it could have a mistake. So I'm going to go ahead and say t is to 5 as 9 is to 3. Okay, so that's the ratio I came up with. Then I cross multiplied, so t times 3 is 3t. 9 times 5 gives me 45, and then I just divide my 3 off, which tells me that this t length right here ended up being 15. Okay, so this was working with triangles and the outside lengths of their edges. What we want to look at on this next one, is the interior angles. So the first thing I want to do is just compare all the angles and see if I can figure any of them out just by looking. So notice my vertices here are labeled M, N, K, and A, B, C, and they're denoted by, notice this angle doesn't have anything in it. This one has 2 lines, and this one has one line. Okay, so if I look at the 1 line angle in both of my triangles, this 1 line angle is 30, this one line angle is 30. So they're both already marked, right? Let's look at the two line angles. So this two line angle K says it's 106 degrees, and it should be the same as this two line angle, which we don't have it listed, right? B is one of the ones we have to find. And since we know that angle K here has to be the same thing as angle B, then that means that since we know K is 106 degrees, that's what angle B must have to be, right? All right, so we know angle B now. Let's see what else we can find. All right, then we have M, which has no angle measure here. And notice A has no angle measure. So that doesn't help me just to compare those. But I should be able to find M, because notice it within this one triangle, I know that this angle is 30. I know that this angle is 106. And I know that all three angles of any triangle add up to 180. So that should help me find M, right? So angle N, which is 30 degrees, plus angle K, which is 106 degrees, plus my third angle, which is angle M, should all add up to 180 degrees. Okay, so all I got to do is take 180 and basically subtract these, right? 30 degrees and 106 gives me 136 degrees, plus angle M equals 180. And then if I subtract that, I end up with angle M is equal to, what, 44 degrees. Okay. All right, so have I found everything I needed? It says to find A, B, and M. We found B and we found M. All right, so the last thing we need to know is angle A. And notice in this triangle, angle A is the unmarked angle. There's no lines here. And the angle in this triangle that has no lines is angle M. So that means angle A has to be the same thing as angle M. And we just determined that angle M is 44 degrees, right? So that means that angle A must also be 44 degrees. Yay! Good deal. Maybe not the worst section of your life, okay? All right, let's look at another one. I want to look up, same idea using similar triangles, okay? But I want to show you one that is an application problem where we have to come up with the triangles ourselves so that we can solve it, all right? All right, so this one says, Nina wants to know the height of a tree in a park near her home. The tree casts a 38-foot shadow the same time that Nina herself casts a 42-inch shadow. Nina is 63 inches tall. What is the height of the tree? Okay, so I'm going to draw a picture just to help. Okay, it says Nina wants to know the height of a tree in a park near her home. Okay, that doesn't tell me anything. The tree casts a 38-foot shadow. All right, so I'm going to draw my tree. Here's my tree. I am not an artist. All right, so here's my tree, right? And I know that when the sun's at this certain point, right, it casts this shadow on the ground, right, that is 38 foot. All right, oh, I shouldn't label that. I should just put this. Okay, 38 foot. So this is where I'm getting my triangle from, right? My tree creates this triangle, okay? So let's see, so all I know about the tree so far is that its shadow is 38 feet, okay? Now it says at the same time, Nina casts a 42-inch shadow. So wherever she happens to be standing, right? Wherever she happens to be standing, she casts a little 42-inch shadow, Okay. And we know that Nina is 63 inches tall. Okay. So that's giving us a triangle from Nina's height and Nina's shadow. Okay. All right, so let's see what we're trying to figure out. Okay. What is the height of the tree? So this is what we're trying to figure out here. I'm just going to label it T. We want to know how tall this is. So because these are similar triangles, and we know that because the sun's angle is at the same for both of them, then we can say that these two lengths are related just the same as these two heights are related, right? So we're going to go ahead and set up our similar triangle. We're going to say the height of the tree, which we're calling T, is the same as the height of Nina, which is 63, and that also relates to their shadows. So notice if I'm using the big triangle here on top, then I need to make sure I use the big triangle length on top also. 38 feet. And then Nina's little height is on the bottom, so we want to make sure Nina's little shadow is on the bottom. Okay, and then we're going to solve. Now, there's more than one way to work this. Okay, notice the way I set it up, I did the heights on the top and I did the shadows on the bottom. I could also do each triangle individually. I could say, okay, the ratio of the pink triangle is height to shadow. So T to 38 is the same as the ratio of the smaller one, which is 63 to 42. Okay, so these are both equivalent. Okay, so it doesn't matter which way you set it up, you should get the same answer. Okay, because notice when we cross multiply here, T times 42 is 42T. 63 times 38 gives me 2,394. And I get that same thing when I solve this one over here. If I cross multiply, notice I get T times 42, which is 42T, and 38 times 63, which again is 2,394. Right? So either way you set it up, just make sure however you do the first fraction, you use the same order over here. Okay? All right, so let's go ahead and finish this out. If I divide off my 42, then I end up with T is equal to 57. And then we want to make sure that we label it correctly. Because if this is a multiple choice problem, sometimes they'll get a little tricky and they'll do something shady, like say inches on one and feet on the other one. Okay, so let's go back up here. Remember, we're looking for the height of the tree, and the tree's dimensions were in feet. Okay, notice Nina's were in inches, and that's okay. She's a much smaller triangle over here, but make sure your label is correct for the one you're looking for. So this means that the tree had to have been 57 feet tall. Okay. All right, so that is the end of section 1.2. So you should now be able to complete that homework assignment. If you have any questions, just let me know.